Kia ora. Hello, I am Nicholas Brook, Principal Engineer on the Cooperative and Automated Vehicle Initiative as part of the Department of Transport and Main Roads, Queensland. I'm privileged to have been invited to present at the TTEC 2021 event organised by ITS New Zealand. However, unfortunately, with everything being locked down at the time, I wasn't able to present, even though I would have just been online. However, I've been invited once again to present in the recorded format. So I hope you enjoy this recording as much as I enjoy putting it together and as much as I enjoyed being part of the Cooperative and Automated Vehicle Initiative. What I want to step through today is a collection of the different projects or pilots that we've undertaken over the past 5 years, and also some of the lessons learned that we think are critical for ITS to progress in both New Zealand and Australia as we reach toward a goal of cooperative and automated vehicles on our networks. Usually this would be a video that I would play, and it really runs through the different facts and features of Transport and Main Roads as a road authority. Being one of the largest road authorities in Australia, being one of the largest states, we obviously own lots of assets and lots of infrastructure, and that's what it outlines, and provide lots of services as well. However, what I think I like to take away from this video is at the heart of each of those different elements is the people. It's our customers, and it's making sure that we can provide a road network that can get them from point A to point B in a safe and efficient and accessible manner. And really that hits also to the core and the heart of cooperative and automated vehicles. And that's why it's been such an exciting project to be a part of for the past 5 years. The first pilot I'd like to discuss is the Ipswich Connected Vehicle Pilot. This is the part I've been working on most closely. And so there we go into a fair bit of detail here and get quite into the technicals of how we prepared, developed, and finally deployed a large-scale pilot. On this first slide, we've just got a few of the partners and vendors that we worked with throughout the project. All of those people were critical to the success, and it really shows the collaboration that's been involved throughout the whole process. And I think, as the name suggests, that really is a key part of the cooperative environment or ecosystem we're building toward, is that it's not just government and it's not just the OEMs or car manufacturers, and it's not just the mapping providers or the device manufacturers. Everyone really needs to work together toward a harmonized set of rules or standards that can actually work together. So the Ipswich Connected Vehicle Pilot had 4 key objectives. The first was to validate the safety impacts and the benefits, so proving that the technology actually provided a level of safety improvement as expected by the use cases. Secondly, demonstrating the technology to build public awareness was trying to get the first touch and feel experience for people in the public with the cooperative, and also this goes for the automated as well, for that technology. So they understand what it is, where the differences are, and so they can actually start having those discussions with their colleagues or friends or family, and through word of mouth, we'll be able to catch on to the trend. So that when these are publicly, commercially available in their next car, they might tweak and go, actually, that is something that I want because I've heard about it or I've seen it in action. Encouraging partnerships and build capabilities is leading back to that previous comment I said about all of this being a cooperation or a collaboration between government and industry and academia. So by working with those various partners, not only are we strengthening our relationship with them, but also strengthening their abilities and technical nous within the ecosystem. And finally, growing the department's readiness. This is a really critical one, because if we see this as part of our strategy moving forward, we really need to make sure that not only are the vendors and our partners ready, but the department itself is ready. And that includes some policies, technical standards, being able to assess the technology, operate it, maintain it, and install it. All will be critical functions if we want to make sure that the performance of what the Transport and Main Roads authorities are putting out to the vendors is actually up to scratch and is usable for their use cases. So the pilot itself was out at Ipswich, which is about 60 kilometres west of Brisbane, for those who aren't aware. It's quite a large area where it's got a really centred city sort of area, then it gets quite rural very quickly. So it was a really good test area because it gave us the chance to experience multiple facets of what a Queensland driver would experience on any given day. So what it allowed us to do is actually approach it from a hybrid communications model where we're able to use use cases that are cloud-based so they can get the messages over cellular, and also some that are using ITSG5 direct from the traffic signals. That's the SPAT map or the traffic light safety use cases. All of the use cases we were developing were aligning to the European standard compliant message formats for ITSG5. And what we were really trying to do is get as many participants as possible. We were targeting 500 public participants that would get this equipment retrofitted in their vehicles. We ended up with 350 for various reasons, COVID being one that it interrupted right when we were about to start installs. However, there are other things about the requirements we needed and criteria for a vehicle or a participant to be suitable for the trial. Numbers of hours of driven kilometres per week is one example of that. The system itself, as I touched on, was a hybrid communications model. So what that meant was the traditional ITS-G5 per the ETSI standards is really focused around the 5.9 gigahertz from a roadside to a vehicle or vehicle to vehicle. However, at the time of us starting the pilot, the central station communication wasn't quite developed. It was on their roadmap. However, we really needed it to be part of our early stages. So we went out on a bit of a limb and started to develop that ourselves with the help of some vendors there. And what that allowed us to do, working with our Australian telecommunications provider Telstra, allowed us to provide 3G, 4G messages direct to the vehicles. So it meant that we didn't have to have penetration of these roadside stations that you can see above the traffic light there at all these various rural locations in order for them to get messages like roadworks warning or back of queue. So that's the hybrid communications model that we undertook. And as you can see, right at the heart of all that is the security service. So making sure we had a security credential management system that was right there and making sure that any message that went within our system was adequately signed and verifiable and therefore trusted by the vehicles so that they were getting trusted and usable messages for their use cases. Speaking of the use cases, these are the 6 that we undertook. So the first 2 on the left, advanced red light warning and turning warning vulnerable road user, were the 2 that worked at traffic lights with the ITS-G5 messages. So that was using SPAT or signal phase and timing messages, and MAP, so the topological description in a data format of how the intersection is laid out in terms of lanes and signal groups. And then we had a road hazard warning, which pulled in the Queensland traffic, which is our local hazard data feed. That brings that in and sends it direct to the cars over the cloud. Back of queue uses our traffic platform's queue detection algorithm and sends those warnings as queues develop on the highways direct to the vehicle and pre-warn them before they approach the back of a queue. The roadworks warning, we had to develop our own mobile application where we're able to put in the different roadwork sites within the area and the approach signs. And again, it develops that message, sends it out over the cloud, and then as the vehicle approaches, it gets a warning and also a warning if it's over the speed limit in the roadwork zone. And then finally, in-vehicle speed. So this required us creating a road network model and an understanding of the speeds all throughout our pilot area, both all 3 static, school zone, which is mostly scheduled, and also variable speed limits. To ensure that all of this was useful to the participants and that the warnings actually were valid and weren't distracting or causing issues for 350 public people within the Ipswich area, we developed quite extensive array of dashboards for our daily operation and maintenance. So we put on a team of engineers who will be keeping an eye on all of the different roadside stations, the cloud infrastructure, and the vehicle stations each day. And as you can see down the bottom left, that's an example of we set up various indicators or metrics that would trigger if different types of messages weren't coming through correctly. And from there, we were able to either contact the participant, check out what was going on, or sometimes we were able to resolve it back of house. And at the worst cases, we found some more systemic issues where we'll be able to roll out a vehicle or roadside software update over our cloud service as well. So our on-road statistics. So this is from May. There's been another 3 months worth of driving since then. So this gives an indication of the scale of messages that we've been able to collect data on. So up to 45,000 messages for advanced red light warning. That was one of the warnings that actually escalated. So if they didn't react to the first warning, it then got to a more aggressive or action taking message. So as you can see there, there's a heads up warning and then there's a take action. Likewise for roadworks warning, there's a heads up message and then there's a take action message. So as that indicates, a really large amount of messages getting warned to the participants. And a critical part of that is for us to be able to get all of the data from each of those different warnings that occurred and the vehicle's trajectory, so their location, their heading, and their movement as they go through each of those different warnings, so that we can actually bring all that back and provide it to our research partners to actually really resolve that validation of safety benefits. And that's one of the key reasons why we needed a central station. So a central station really allowed for that data to be not only brought back or sent out to the vehicles in the form of messages that they could warn based on, but also to bring those messages back and bring back a few of the other bespoke message sets that we created, which allowed us to not only track how the participants were driving so that our behavioral driving study had some ethical legs behind it, but also it allowed us to look at the station health and really helped us with our operation and maintenance by being able to get lots of information about their GNS quality, the cellular quality, the uptime of devices. So that was all really quite critical to having that central station, particularly with such a large pilot in such a rural area with various driving tasks. Other pilots that we'd researched before we started had done things like having pit stops where all of the vehicles would have to go back to extract the data. And we just thought that that seemed a really large overhead for us and the participants. So that was one of the key reasons about building this data hub or data lake as it was to receive all the data back and then running our analytics through it so that we can actually start to make, yes, operational decisions on the fly, but also make assessments of the data quality as well. The other feature I touched on earlier was the ability to do over-the-air software updates or configuration changes was really helpful. As we were developing, we found that there was some of the configuration for things like back of queue that weren't as good as or optimized as we would like. So we're able to optimize those with no impact to the participants. So that was a really big benefit for us. A critical part of the central station was to allow the vehicles to be able to just download a set of information that was relevant to them at the time of where they were driving. So to enable this, the central station built out a geo-messaging facility. So to start with, the vehicle would load up, connect to the central station, and it would say, oh, okay, this is where I am. I'm in Australia. So then once it was located in Australia, it would go, okay, here are your options within Australia. Here are the different tiles, as they were called. So then it would go, okay, I'm in the Queensland tile. And then once it located to there, it got the options of the tiles within Queensland. And as you can see there, we've got all the different tiles within Queensland within the Ipswich pilot. And as it moved between tiles, it was actually able to preemptively download tiles within a kilometre buffer of the next tile. So as soon as it crossed, it was a seamless transition for the participant in terms of the speed limit display, or if they had warnings that were crossing over the border of 2 tiles. The central facility itself is actually built up of a data lake, a monitoring and reporting service. So that was the dashboard, that was what built out to the dashboards that we talked about before. But it also had a spatial service which made the messages spatially relevant based on the information it was provided, as well as the messaging center. So turning what was either just JSON information or quite raw sort of data sets into actually CITS compliant messaging was a really critical component of that. And then finally, the central station part of the central facility is the actual broker, which allows it to send messages to the vehicle stations, the roadside stations, or any other station that we were able to provide a subscription certificate to. All of the messaging process was also secured within the SCMS as well. To give you a context of how much work that broker ended up doing, the messages and volumes per day, huge. So we were pushing out 400,000 messages a day to the vehicles, and that was CITS messages. On top of that, it was also doing what's called real-time kinetic messages, which is positioning augmentation. So the vehicles would use that to make sure that they were lane level accurate all the time. So that's 1.5 million of those messages sent to vehicles per day. We have 70,000 health messages, both from vehicles and roadside, sent back. So every minute they would log their current health. 1 million safety evaluation messages, 2 million messages published to the broker. So that's over 6 terabytes of safety evaluation logs since the pilot started. And that was back in May. So we're probably close to 9 to 10 terabytes now. Another critical component of the Ipswich Connected Vehicle pilot was the effort and the time that we put towards making sure that the system was secure. So we put in a security credential management system, aligning with the European standards. So what we're intending to do here was to make sure that any messages that the roadside or the vehicles were sending to each other, or even the central station in that case, when received by another one of the stations, particularly the vehicle station, it would trust that message and not display something that would be erroneous or wrong or dangerous to the driver. So what we don't want to do is get to a point where any person could sit up with a laptop and pretend to be a traffic light and say that the traffic lights are red or traffic lights are green, and the vehicle to be able to receive that message and then actually act on that, because that's to a point where it really degrades the point of the trusted ecosystem. So this SCMS is set up similarly to how a JP would be set up. JPs in Australia are people who verify documents. So a document, an original document like a birth certificate, you could take into a Justice of the Peace or JP, and that they can give a copy of that a stamp. So similarly to that, that's how the SCMS works. It effectively goes, I'm stamping this message and saying that anyone now who sees this message knows that it's been verified by someone who's been given an official permission to verify this. And that's the same way that this system is set up, and it really ensures the full CIA, so confidentiality, integrity, and availability of security. Here is a more graphical diagram of what I was describing. So this is a setup very similar to, it's quite common to most ITS PKI architectures, and it aligns with the ETSI standards. What we have here is that the assumption is that Australia has one root authority, and for now, as far as we're aware, we have the only one that there is. Whether that sits in the long term, I'm not sure, or what the strategic or policy direction of that is, or if it's an Australian based one or it's Australia and New Zealand shared one. However, that route authority would then provide a trusted, I guess, ability to somebody such as a enrolment authority who might be a vehicle manufacturer, who are then able to give a vehicle a stamp to say this vehicle can now ask for certificates. So then that vehicle itself can go out and reach out to the AA whenever it needs, and that AA will go, okay, I can see that you've been verified by the EA, the enrolment authority, so yes, you can get those certificates you've requested, and then that vehicle will use up those certificates. The way we've set ours up is with pseudonyms so that they change their station identification every 15 minutes, and that allows those vehicles to not be tracked. So by changing what station identification it stamps any signed message with, no one could really start to track a trip because it would be changing every 15 minutes, which does mean its certificates run out. So at the end of each week, it actually reaches out to the AA. Each vehicle reaches out to the AA and requests another bundle or another week's worth of certificates. And it just keeps doing that time and time again, reaching out through the web and doing that. So what really point out that route authority, that becomes your critical piece of infrastructure. And to give you an example of how rigorous the system around that is, we actually had to send one of our employees over to America to be part of a key ceremony where they physically meet in a room and they check off a list of requirements to make sure that when that route authority is set up, that the only people who could have access to the keys there are us as the customer, TMR, and the ISS as the people who develop it and have their own contracts in place to ensure security. So it really is quite a rigorous and secure system that's been set up, and it's not dissimilar to a PKI system that your bank accounts or something may utilize. Moving on to development. The development part of the entire pilot was really quite critical. We had so many different moving parts, vendors, collaboration to have happened, which really made it critical to co-locate as much of the team as possible. Whilst many of the vendors were based in various parts of Australia, by having them co-located at TMR, it allowed us to be agile through our development and testing processes. It also meant that we could, if issues such as with the standards, when standards went standards superseded other standards, we're able to rectify that as quick as possible. It allowed for continuous integration and also continuous delivery. So always testing and checking against each other and making sure that changes worked. So the lessons we learned from conducting such a large scale project is that they really are important. To be able to prove things at scale mean that you don't just get a one or two pieces of evidence and be able to make a call on a piece of technology. By running it at this larger scale, there would have been probably 20 or 30 different issues that we wouldn't have found until quite deep in or with such a large number of participants involved. You get to find a lot more edge cases and you get a lot more data that really can be used in a variety of ways, not only to prove your original hypothesis, but also for future options analysis and developing out your next steps. Making sure that you have sufficient schedule and development time for R&D projects, particularly when you have that collaboration across vendors, where you have critical integration points, you really need to allow more time for that. And another one we've learned is that building in configurability of things such as being able to change the use cases parameters so that we can change how early or late it actually alerts. Because a lot of the time things look really good or sound great in theory and it seems like the right number to use. But when you're actually in the vehicle feeling it for yourself, you can very quickly pick up and go, oh, that was a bit late or that's a bit early. And by being able to make that configurable and tweak that through whatever system you have simply, it means that you can get a better experience for the participant or whoever your end user is. Making sure that the quality of the data is able to be verified, but then used immediately, not only for data analysis, but also for visualization. Being able to put these statistics onto slides to show our management, or to be able to look at it in a daily dashboard where we can very quickly see if something needs improvement, was critical to be able to make sure that that integration was working and that there was that continual improvement throughout. Making sure that we use testing as a good driver for development. So building out your requirement set, setting up your test plan, and then matching against that. Understand where you're not meeting those requirements and working backwards from whether that requirement's still needed. And if you don't end up meeting that requirement, making sure you document why and what it is, so that when you finish the pilot or project, you can then look at it for the next steps of how to evolve out of that to a more mature system. And finally, understand what the end user is trying to actually achieve, what you're trying to achieve for the end user, sorry. That's what you want to always keep in your mind when you're checking against your test reports. So some of the lessons learned for the future of pilots from the pilot for the future is that for a government, we really need to make sure these systems can support the performance requirements for vendors. We had Lexus as a partner once for a large portion of the pilot, and that was really important to be able to be in meetings and talk very openly and honestly about what they need from us as a road authority for them to look at this as a worthwhile investment to put within their fleet. They really need that level of trust of the availability and of the messages, the low latency, the accuracy, so that when they end up building out use cases into their vehicles for their end users, that they can do it with a level of trust that they go, this will work for the user. It's really the first time in a while that a vehicle manufacturer is going to be so reliant on data received from a road authority. So I think that if the more we put as road authority managers or owners into that to make sure these performance criteria are hit and made, I think that will really smooth that, oil the gears to allow industry to really get behind this and get involved. The next project I talk about, the cooperative and highly automated driving pilot, is a really exciting merge between the two technologies at the forefront of the ITS mind at the moment, being cooperative vehicles and automated vehicles. So it's a pilot that really brought together both aspects of that in the form of a vehicle that was actually a level 4 automated vehicle that was able to move around public roads at 50 kilometers per hour, whilst also being able to record heaps of research data and also work on off-road safe test tracks to really prove out some of this cooperative ITS convergence with AVs. I wasn't a project manager on this one. It was actually Amit Trivedi. And so I hope to do it justice. However, afterwards, if there are any questions, I'll be able to refer them on to him. Highly automated driver pilot, it involved two critical research vehicles. So the first one came slightly sooner and was retrofit with AV style sensors. However, it wasn't actually controlled. It wasn't an AV in the true sense of it being actually controlling the vehicle. But by using those AV level sensors, we're able to get out there on the road and actually start recording some of the data that will be needed and start doing some of the reports on the infrastructure abilities to suit an AV or AV equipment before the Zoe 2, which is our automated vehicle, arrived. So Zoe 2 was built over in France by Vedicom, which is a French research institute, which includes Renault, which is the Zoe vehicle itself. So they take the core of the vehicle and they retrofit it with all of the AV sensors and equipment and a lot of hardware in the back that feeds data and records data, so that it truly is a full research vehicle. It's not just a shuttle or a vehicle that's for show. The power of the Zoe 2 is from the data that can collect from its various sensors and cameras, and then it can compare them all and produce some really impressive reports about how AVs will be impacting the Queensland roads or Australian roads and Australian New Zealand roads in the future. So to add to that, as the name suggests, it's also cooperative. So it also has a CITS station built within it so that it can actually receive messages like spat, map, and denim as our output as part of the Ipswich Connected Vehicle Pilot. Amit himself actually went over while they were building the Zoe in France. So he's actually had first-hand experience in how they developed the product, the testing while they were in France, and then bring it all the way back over. And so since it's been in Australia, it's been doing a fair few different projects that they've broken up into different work packages. So one of the work packages is looking at the driver handover, so actually having it drive by itself with a person or a participant in the front seat, and then at various points it will just prompt them to take over, and it will then gauge from that how the driver takes over control and how quickly they can turn off from the action they were doing, such as reading or watching something on their phone, to then taking over the vehicle safely. I've done that one myself. It was quite a different sort of experience watching some basketball on my phone, and then being told, take control of this vehicle. Thankfully, there was always a safety driver next to us, so you never felt you were truly at risk. But it was a really interesting first taste of how that might act out in the future. Other studies that they've done is interaction with other road users. So whether that be cyclists riding past and how it interacts with that, how it interacts with trying to simulate animals by using things like the giant office bouncy balls. Another study was the physical infrastructure needs, so taking it out on the actual road network and then analysing from the data what signs, what lines it was able to recognise, what it wasn't. And that includes a more recent trip all the way out to Charleville for the show out there, which is even further than Ipswich and includes dirt roads, grid crossings. So it was quite interesting to see it out in an area which isn't seen as one of those for early domains for AVs. The interaction with the digital infrastructure, linking in with the cooperative ITS that's been built out through the ICVP and particularly at the Mount Cotton Research Centre, where we're able to safely test off-road. And that was able to do a variety of different cooperative use cases. And then also a key report that they put out in the last 6 months is the identifying government's role in HD maps. So understanding what could be put into the vehicles prior to give them an enhanced vision of the road before they're even at the location. So for any of the drives that the Zoe 2 has done on the road with normal traffic, which it has done a few now, all of its paths are pre-mapped out through a HD maps process. So it's at least aware of its surroundings and where it's trying to go to. This has been two very exciting parts of it, I believe, is the use of the cooperative ITS messages. So the first one being a vulnerable road user. So to simulate this, they actually use some sight screen at the test site to block off where the pedestrians can be seen. So that way we knew that the AV couldn't actually see or sense the pedestrian themselves because all of its vision was cut out, which is trying to replicate a real world environment where, such as in this diagram, where a truck might be actually occluding the view of the sensors. However, because the intersection was equipped with a roadside station, it was broadcasting there was a pedestrian on that crossing that it was trying to turn across. So as it approached, it rightfully slowed down, snuck around the corner, and then basically stopped until it could verify through its sensors that that crossing was cleared. So that was a really impressive one. And the second CITS use case that they've tested out is also a roadworks one based on denim. And that is using broadcasting a denim and saying, for instance, that the left lane is closed, and that was the lane that the Zoe 2 was traveling in, and it safely navigated across to the next lane. And they did various iterations of that where it actually had to not just leave that lane, but leave that lane while negotiating and merge with other traffic. And once again, by getting that prior information, it was actually able to do that really safely and merge in quite well. prior to basically getting right to where the roadwork started, and having to stop and go, I don't understand what to do here because my senses just say that there's a sign saying stop. So that really, I think that last slide really summarizes where these two types of technologies converge toward a set of use cases that add a huge advantage to the people of New Zealand and Australia in terms of a safer, more efficient, more sustainable road network, where cooperative automated vehicles are just one, and that you can use road authorities' information that is trusted to really enhance that AV experience in the future. Thank you very much for those who stuck around, and I hope that this presentation has been enjoyable to you. All of these projects, I think, have been riveting for us, and we think add a really, really great value to the ITS industry more broadly. And if you'd like to understand more or learn more from us, feel free to reach out on any of those networks there. Look myself or Amit up on LinkedIn, and I'm sure we can either respond to your questions or direct them where they need to go. Or if you'd like to reach out to the ITS New Zealand coordinators, they'll also have my contact details. So thank you very much, and I hope to see you all in some sort of real person or live environment soon. Kia ora.